Let me start recording. So we are keeping the distance of separation constant, the area constant, and we are only inserting a dielectric between the plates. We are saying our observation is that the leaf is observed to collapse, meaning to reduce in its divergence. Remember, originally it was divergent. The reason we connected the gold leaf to a charged capacitor. So the plate is already having a positive charge, or it is having a charge. Once you connect a gold leaf electroscope, the electroscope should also get charged by conduction. And therefore, we expect the leaf to be divergent already. So what are we saying when we insert the dielectric? The divergence reduces. At many times we use the word collapsing. So it should not be any point of contention here. We use the word collapsing, meaning a reduction in the divergence of the leaf. So it is observed to reduce, but since we know that divergence of the leaf is a measure of the PD between the plates, then a fall in the divergence means a reduction in the PD. But again, we know that the PD is related to the capacitance by this relation. What does that one mean? Since V has reduced, C has increased. Since the relation is an inverse relation, a fall in PD will mean an increase in the capacitance. So the conclusion here would be that inserting a dielectric between the plates of the capacitor caused an increase in the capacitance of this capacitor. And that's what we have been investigating. I invite any questions if anyone has, before we look at something different. We could even ask about the first experiment where we talked about effective area. I guess there are no questions, so we can go on. Yes, please.
Chami, I beg your pardon on the effective area, if you don't mind.
Effective area, we said when we start with the capacitor. We said we can do it in two ways. Either I start with the plates completely facing each other so that I have maximum effective area, and therefore I ensure that the capacitor I'm using is charged, so I put a positive charge on one plate and the other one we said is earthed. So since this plate is charged and I connect it to a gold leaf electroscope, then the gold leaf electroscope will also get charged by conduction. It gets charged by conduction, and therefore the leaf diverges up to some point, and we said we can note that the divergence as theta. Now we slide one of these plates vertically upwards or vertically downwards. The essence is to reduce the effective area. When I slide one up and one down, okay, I keep one constant, but I slide this one, say, downwards. What I'm calling the effective area will only be this part now. Only this part of the plate and this part of the plate are the ones forming a capacitor. This one here, from here up to here, is not part of the capacitor. From here up to here is not part of the capacitor. The capacitor will only be this part. That's why we talk of effective area. Whereas here it is the whole part, because all of them are facing each other. Here they are only facing each other partly. So those parts facing each other are the ones forming the capacitor. So in this case, we have reduced the effective area, or what we call area of overlap, whereas here the area of overlap is large. So we said when we slide one plate vertically, either upwards or downwards, The observation is an increase in the divergence. When we look at the leaf, it diverges more, maybe some other deflection, theta prime. And we said the observation is that theta prime is actually greater than the original theta, meaning there has been an increase in the divergence. And since the divergence is a measure of the PD, yet the PD is inversely proportional to C, an increase in V implies a fall in the capacitance C. So since in this experiment, when we decrease or we reduce the effective area, we see that the leaf diverges more. It means there has been an increase in the PD, which implies a fall in the capacitance. The conclusion becomes when we reduce the effective area, the capacitance also reduces. Contrary, if we increase the effective area, we shall be increasing the capacitance of the capacitor. I hope that is enough. John?
Yes, teacher.
Good. Have another question? Yes.
In these experiments, when we are determining the distance of separation and inserting a dielectric, we are starting with the plates are restored in position. Does it mean that when we are given when we are asked to determine an experiment of distance and inserting a dielectric, does it mean we start with the plates are slid vertical, upwards or downwards?
Exactly. Now, supposing the question was, describe an experiment, investigate the effects inserting a dielectric between the plates of a capacitor. For example, this is what we have been describing. But the question is specific. They are not telling us to go through all the three factors. They are specific to only one factor, and that is inserting a dielectric. Do we again start with the plates are restored? We are saying no. We are using this statement because we are referring to some work we did before, and we are looking at this one as a mere continuation of the other. But if it is like this, probably if it is with the aid of a diagram, then there will be need to draw our diagram again. We first draw the diagram. Still one is, the other plate is aft, and then the other is connected to a gold reflectoscope. We shall have the diagram like that. And then we start from here. We start from here. That we are keeping the area and the distance of separation between the plates constant. That one is a mark. Because we know that these factors, if you change them, they will also have an effect on the capacitance. So it may not necessarily be that it is inserting the dielectric that caused the change in the capacitance. That's why we want to keep all other factors constant and we change only one. So it will be important to start with, don't forget to be using a charged capacitor. So we start with keeping the effective area and the distance of separation constant, the dielectric is inserted between the plates of the capacitor. I hope we are seeing the picture of what we are talking about. You don't start the experiment as if it is a continuation of something. No. This is an independent question and it is about inserting a dielectric. So there's nothing like we restore the position. No. That one would mean you did other experiments earlier. But the question requires you to do only this, not to start with the others and now end with this one, okay? Thank you for that question, by the way. It had skipped my mind. It was important to guide students about it. People may think every time we are asked about distance of separation, we have to first restore. No. We are restoring because this was a continuation of some previous work. But if it is specifically the experiment we want to do, we don't start with restoring. We right away go to the procedure leading to the conclusion about that specific factor. Thank you. That was who? It's not Lenny. Mama Lenny, can you have the energy to ask? Okay. We want to look at explaining the effect of a dielectric. Is our subheading. Before we look at studying, doing the experiments using what we call the reed switch, let's first look at explaining the effects. Explaining the effect of a dielectric on the capacitance of the capacitor. Is this the same as investigating the effect?
Investigating the one to see it. But here explain has already happened. We're trying to show the person.
Adoyo is telling us that investigating is like we are looking at what happens when we do this. But now explaining it is that the event has already happened, but we are explaining why is it happening that way. Is that untrue, Irina? Some of you have gone digital. Irina could be mentioned as Irina. So how do you read it? Irina or Irina? Irina. Starting. Middle. Okay. People don't want to study in the evening. Thank you. Irina. Irina. Now I wonder how you'll pronounce Mirembe in that style. Will it be Mirembe? Mirembe, say something. Is the explanation given by Adoyo the correct one? That investigating, we are looking at what impact, what effect it causes. But now explaining, we are looking at why does that effect that happen that way? Is that untrue?
Yes, teacher, it's true.
Correct. Now, later after explaining this one, I'm going to outline here some questions which confuses students always. They ask you for the experiment, for you explain this. When they ask for the effect, explaining the effect, for you answering, giving the experiment. We shall look at a sample of the question. If I forget, you remind me. Okay. Those who are here to the beginning, we watched a video, and in that video, they were trying to show us the factors that affect the capacitance of a capacitor. But I'm interested in one part. I don't know if that video is still here. Let me see whether I can quickly find it. It is not there anymore. It was this one. Some people have started dancing already. Let's watch this video briefly again, and you see what I want to explain here. I will skip some parts. Battery. Let's increase your what this one is saying is that when the area is large, or when the effective area is large, it means we have enough space to push more electrons on the plate, meaning this plate will have enough space to store more charge. And every time the blue ones are representing electrons. Remember, positives don't move, so there are the blue ones which are moving. So as more blue ones, or as more electrons come to this plate, more electrons are leaving this one, meaning you are creating a positive this side. The plate is becoming more positive as this one becomes more negative. So the bigger the area, the more space you have to store more charges. And that's the implication of this. My interest is on inserting a dielectric, so let's move up to that point. Good. Let's look at this point. It is the one I'm interested in. We start it. You should be seeing how the molecules are coming in. Look at the arrangement of the molecules when that dielectric is being inserted in. They are randomly arranged. Some blue ones are the other side, the red ones are facing this side, but what happens? Let's continue. I hope they will change it again and we see it in a better way. I'll repeat. At this point, if you realize those molecules between the plates, originally the blue and the red were randomly arranged. The blue would be this side, the red is this side. Another blue is up, the red one is down. But after inserting it in the dielectric, I hope you realize that that was when they are still random. For example, if you look at this one, blue is facing that side while red is this way. The next one, blue is this side and the red is the one the other side. But after inserting it, what happens? They have aligned themselves. Do you realize that all the blue are on one side and all the red are on the other side? Are we realizing that?
Yes,
Yes.
teacher.
Good. So that's
Yes,
what
we are realizing.
we want to explain here now. So what happens when, if this plate is negative and this one is positive? When you insert a dielectric in here, that the molecules within this dielectric themselves get distorted. They get rearranged. First of all, they were random, but what happens? They get polarized. So instead of being circular, they acquire what we call oval shape. Originally from chemistry, we know that we represent an atom with a circle. And within this circle, you have energy levels. The center is the nucleus, which is positively charged. And then you have electrons in orbits surrounding this nucleus. But when you insert such an electron or such an atom within an electric field, remember there is an electric field between the plates. Since one is negative and another one is positive, there is a potential difference already, meaning there is an electric field. The electric field will have to affect this atom here by causing one, the positive plate will have to repel the nucleus which carries a similar charge, whereas it will try to attract the electrons towards itself. As a result, the shape of this atom is going to be like changing. If this side is positive and this side is negative, then we are going to have like an oval shape. Instead of a circle, we have an oval shape where the positive will be repelling the nucleus away from itself. So instead of the nucleus being at the center, it is now being repelled towards the other end. As the electrons will tend to be attracted on one side. Are we getting the point? The positive plate tries to repel away the nucleus which carries a similar charge. So the nucleus tends to be on one side. And then the electrons will also be repelled by the negative plate. It will repel all the electrons will go the other side. You can explain it as being attracted to the positive or being repelled by a similar negative charge. Just like with the nucleus, you can say it is being repelled by the positive plate or it is being attracted by the negative plate, either way. So the orbits behave as if they are like rubber bands, and therefore they appear to be in a stretched mode. But because remember this, what we are bringing in here is an insulator. These electrons are not free to leave the orbit to go and neutralize the plate. They cannot. They are bound electrons, or they are bound charges. So they can only get closer to that plate, but not neutralizing it. Why? They cannot leave this atom, since they are insulators. Insulators don't have free electrons. The electrons are not free to move, so they will remain. So in such a case, when it acquires an oval shape, because of that transition that has occurred, we say it has, the molecule has been polarized, or sometimes we say it has been distorted. Why? It was circular, now it is becoming oval because of the rearrangement of the charges within it. So we want to say these mulches within here will have to rearrange, causing the negatives there and positive to this side. Positive, negative. I don't know if we are able to see those charges within the oval shape. Are we able to see them? Let me just try to magnify what we are drawing there, but we shall continue this diagram. Like I have one plate here, and another one is here. The atom has been distorted, so it has acquired an oval shape. While this atom, this side is also distorted to acquire an oval shape. Since this plate was negative, and this plate is negative, is positive, positive, negative, this one will attract the negatives towards itself, and the positive will be repelled on the first side. Likewise, here the positive will be this side, while the negative will be far aside. As a result, if you have any other in here, any other atom, which is also distorted, will have its positive this side and the negative this side. So that by mere neighboring at this point, and this one also neighboring here, the effect in the middle there tends to cancel out because a negative is neighboring a positive, negative neighboring a positive. The end result is like we have positives only aligning around since we have seen that these effects will be cancelling in the middle here, the end result is like we have only positives along here and the negatives along here. Do you see that? This negative will be like neutralized. We don't say neutralized because these are again bound charges, but the effect seems to be like they are neutralizing each other, like this. So we are remaining with only the negative on the outside and the positive this side. The middle is like neutralized, there is no effect. The end result is that it's like this material now becomes another capacitor, having this side positively charged and this side negatively charged. I want us to realize that since originally the plates were themselves charged, there was an electric field which was facing where? From the positive to the negative. But after inserting the dielectric, we see that we are again creating a positive charge along here, along this line, and a negative charge along this line. Meaning we are creating another electric field between the faces of the dielectric, which will be facing where? From positive to the negative. So this effect, we will have another field between the faces of the dielectric. If this electric field was E naught, the new field here is E. What we shall call the resultant is going to be the original electric field minus the new field. Why minus? Okay, this one was facing towards the left. Now this one that is created is facing towards the right. So it's like there are two opposing electric fields. Remember, electric field intensity is a vector quantity. We are interested in the direction. So since this field was facing this side, and this one is facing this side, the resultant is the difference. So what does that one mean? It means that the original electric field intensity without the dielectric is greater than the new resultant. Is that untrue? And this one means that E, not the original field, when there was no dielectric, is greater than the field intensity, what we call the resultant, after you have inserted the dielectric. Is that untrue? Because the resultant is the original itself, but minus something. So you are reducing it by something to get the resultant. So it means that E naught alone is greater than ER. Is it true, Namuyanja, Theopista? Namuyanja, something like that.
Yes, teacher.
There's this girl, I want to pronounce the name, but it is hard. AMANRH. What is that name?
Amana.
Ah, it is also African.
Swabra, teacher, tell you Swabra.
She's called Sabra. Wow. Okay. We shall not be mentioning you. We shall not give you a chance to say something. Let me mention.
Teacher. Teacher.
Yes. Yes. Hey.
Teacher, I wanted to ask you to help me repeat those arrows of Inot and I didn't understand.
We shall start from there next time. No? Thursday. We are already 8 minutes beyond our time. We shall start with that point and we re-explain it. I know there are some people who switch off once it is time. In psychology, we call it classical conditioning. You told the mind that at 5 is when we are ending. Once you go 1 minute beyond 5, that thing will not be picked ahead. You see, even the numbers have reduced to 14. So we shall start with that one. I think on Wednesdays when we have some lesson. The one for Mr. Mlond, I think, if it is not mine. I want to wish you a nice evening and good night.
Bye, teacher.
Right.
Thank you for teaching.
You're welcome.
Teacher, goodbye.